Welcome to another deep dive.
Oh, this is a fun one.
It is. Today, we're diving into the world of optics. Light, mirrors, lenses, all that good stuff. We've got some physics textbook excerpts to work with.
Classic.
Right. So, get ready to explore how light does its thing. We'll break down the cool parts and connect it to stuff you see every day.
Because let's face it, optics are everywhere.
Exactly. Think about it. How do we even see? Why do mirrors reflect? And how do glasses actually work? By the end of this, you'll know not just the basics, like reflection and refraction, but you'll also understand those curved mirrors in cars, how a magnifying glass focuses light, and maybe even crack the code of your eyeglass prescription.
Well, to kick things off, the way we see boils down to how light behaves. And for the most part, light's pretty straightforward. It travels in straight lines. Like, think of a beam from a flashlight.
Yeah, the textbook uses those sharp shadows you get from a small light source as an example of that straight path. It's like lights on a mission, always taking the shortest route.
Precisely. But, and here's where it gets interesting, light can sometimes bend around really tiny objects, kind of like a wave hitting a small obstacle. That's called diffraction, and it kind of shows us the wave-like side of light.
Ah, so light isn't always so straight-laced after all.
Well, for this deep dive, we'll stick with the straight line model. That's mainly what our source material focuses on, and it helps explain a lot of the cool stuff we'll be talking about.
So for now, we'll imagine light as like a really determined traveler on a straight path. But sometimes it bumps into something and has to change direction.
Right. And one of those things that causes light to change direction is reflection. We usually think of mirrors, but reflection's happening all the time, everywhere.
The textbook reminds us about those two laws of reflection. Remember those? The angle it hits a surface equals the angle it bounces off, and it all stays in the same plane. Pretty basic, right?
Totally. But here's the catch. Those laws, they don't just apply to mirrors. Think about it.
Oh, I see what you mean.
You see reflections in a calm lake, a shiny car, even a polished floor. Any surface can reflect light. It's just that some surfaces do it better than others.
So a mirror just gives us a really smooth surface for that reflection to happen in a more organized way.
Yeah, exactly.
And when it comes to mirrors, things get extra interesting when the surface is curved. We're talking concaves and convex mirrors, like the curve of a spoon.
Right. And the textbook uses that spoon analogy to introduce concave and convex mirrors. A concave mirror, like the inside of a spoon, curves inward, while a convex mirror, like the back of the spoon, curves outward.
Got it. So we've got these curved mirrors. How do they actually work? Like what happens when light hits them?
Okay, well, first, to really get how they work, we need to know a few terms. Imagine slicing a thin piece off a ball. That slice is your spherical mirror.
Okay, picturing it.
Now, the center of that ball would be the, what's it called? The center of curvature, right?
Center of curvature, yeah. And the line cutting through the middle of that slice, the one connecting the center of curvature to the mirror's surface, that's the principal axis.
You got it. And the point where that line meets the mirror's surface, that's the pole.
So we're basically mapping out the anatomy of a curved mirror.
Exactly. Now, let's think about what happens when light hits those curved surfaces. Remember that experiment where you used a concave mirror to focus sunlight and burn a piece of paper?
Oh, yeah. It felt kind of magical how that concentrated light could make so much heat.
It's a simple demo, but it shows us a key thing about concave mirrors. They converge parallel rays of light, meaning they bring them together at a single point called the principal focus.
So it's like the mirror's gathering all that sunlight and squeezing it into one tiny spot. No wonder it can get hot enough to burn.
Exactly.
And this isn't just for science experiments, right?
No, not at all.
This converging thing is used in real-world stuff, too, like solar furnaces, right? Those massive dishes in solar farms are basically giant concave mirrors.
You got it. They concentrate sunlight to create some serious heat, which is used to generate power. Pretty amazing.
And even something as familiar as a car headlight uses this. The bulb is at the focus of a concave reflector to create a beam of parallel light, illuminating the road.
Exactly. You're catching on quickly.
Well, it's fascinating how something so seemingly simple, a curved mirror, can be used in so many different ways. But it gets even more interesting when you think about how these concave mirrors create images.
Right.
The textbook digs into that whole image formation thing. It even has a table listing different scenarios based on where you put an object in front of the mirror. And that determines what kind of image you get, right? Real or virtual, magnified or diminished, inverted or upright.
Yeah, it can get a little complex, but we can break it down.
So basically, depending on where you put the object, the mirror plays tricks with the light and creates different effects.
Precisely. For example, in that burning paper experiment, the image of the sun made by the mirror was real, meaning it could be projected onto a surface. But sometimes the image is virtual, appearing behind the mirror, and it can't be projected. It's like an optical illusion.
Okay, I'm intrigued. Let's pick one of these scenarios, maybe one where the image is virtual and enlarged. Can you walk us through how that works? Maybe use a ray diagram or something.
Sure. Let's say the object is placed between the mirror's pole and its principal focus. Now, to see how the image forms, we use a ray diagram. It's basically a way to trace the path of light rays as they hit the mirror. So we draw a few special lines, or rays, from the top of the object to the mirror. These rays help us see how the light's bouncing and where that image will end up.
Okay, got it. So what are these special rays?
All right, the first ray goes from the top of the object parallel to the principal axis, and when it hits the concave mirror, it reflects and passes right through the principal focus, or F.
Like it's taking a detour through that focal point. Gotcha. What about the second ray?
The second one passes from the top of the object through the center of curvature, C, of the mirror, and since it's hitting the mirror head-on at a right angle, it bounces right back along the same path.
Okay, like a perfect rebound. Straight back from where it came. What about the third ray?
This one goes from the top of the object straight to the pole of the mirror, which we labeled P. It bounces off at the same angle it hit, just on the other side of the principal axis.
So we've got these three rays bouncing off in their own special ways. But where does the image actually form?
Now here's the thing. In this case, the reflected rays don't actually meet in front of the mirror. If you extend them backward, behind the mirror, they seem to come together at a point. That's where our virtual image is.
Wait, so the image is like behind the mirror. That's trippy.
It is. It's an optical illusion. The light's not actually coming from that spot behind the mirror, but our eyes trace those rays back, and that's where they seem to meet.
So it's virtual, meaning it can't be projected onto a screen like that burning paper experiment. More like a phantom image our brain makes up.
Exactly. You got it. And in this case, since the image is farther from the mirror than the object, it looks bigger too.
Oh, I see. So that's how those makeup mirrors work. They make a bigger virtual image of your face so you can see better. Clever.
That's a perfect example. Concave mirrors and their magnified virtual images. But concave mirrors aren't the only curved mirrors out there. We also have those convex mirrors, the ones that curve outward.
Yeah, the textbook mentioned those being used as rear view mirrors in cars. Is it just because they're curved? What's the advantage?
It's not just about the curve. It's about the type of image a convex mirror makes. Convex mirrors always give us images that are virtual, upright, and smaller than the real thing, no matter where you put the object. But the key for drivers is this. A convex mirror gives you a much wider field of view.
Oh, right. So you can see more of the road behind you. That makes sense, for safety and all.
Exactly. It lets drivers see more of what's happening around them, cutting down blind spots and making it easier to see other cars, bikes, or people walking.
And the source material even mentions this cool example of a convex mirror in the Agra Fort in India. They placed it so it shows a full view of the Taj Mahal, even though it's pretty far away.
Yeah. That's a great example of how convex mirrors can capture a wider scene than flat or concave ones. Like they're made for panoramic views. Think of those security mirrors in stores. Those are convex too. It lets cashiers see a whole bunch of aisles at once.
So from cars to security, those unique properties of convex mirrors make them super useful. But we've been talking about reflection this whole time. What about that other way light changes direction? Refraction.
Refraction. Now that's where things get really wild. Refraction is when light bends as it goes from one medium to another, like air to water or air to glass.
Yeah. The textbook has some good examples, stuff we've all seen, like a coin at the bottom of a pool seeming closer to the surface than it is, or a straw in a glass of water looking all bent at the waterline.
Those are classic examples. It all comes down to how fast light travels in different mediums. When light goes from a less dense medium, like air, into a denser one, like water or glass, it slows down.
So it's like light hits the brakes when it enters a denser medium. But why did that make it bend?
Imagine driving from a smooth road onto a patch of sand. The wheels that hit the sand first slow down, right? Causing the car to turn a little bit. Similar thing happens with light. When it hits a denser medium at an angle, the part of the light wave that enters first slows down, making the whole wave bend.
Oh, I get it. That's a great analogy. So the bigger the difference in speed between the two mediums, the more the light bends. And this difference is what we call the refractive index, right?
Yes. The refractive index, or N, of a material tells you how much it slows down light compared to its speed in a vacuum. A higher refractive index means light travels slower in that material and bends more when entering or leaving it.
The textbook has this table with the refractive indices of different materials.
It's kind of cool to see how they're all different. Like, it says kerosene has a higher refractive index than water, even though it's less dense. That seems a bit weird.
Good observation. It shows that optical density, which is about how much a material bends light, isn't the same as mass density. The way kerosene molecules are arranged, they slow down light more than water, even though they're not as tightly packed together.
So it's not just about how squeezed together the molecules are, but also about how they mess with the light.
Exactly. And that's really the key to understanding how lenses work.
Just like with mirrors, we've got two main types of lenses. Convex, which are thicker in the middle, and concave, which are thinner in the middle.
Yep, that's right. And their shape determines how they affect the light. Convex lenses, like that magnifying glass, they converge the light, bringing those rays together. Concave lenses, on the other hand, they diverge the light, spread it out. The source material mentions an experiment where a convex lens is used to focus sunlight and burn paper, just like that concave mirror we talked about. How is that different from the concave mirror experiment?
They both focus light to a point, but they do it differently. The concave mirror does it with reflection, bouncing the light inward. But a convex lens uses refraction. It bends the light as it passes through those curved surfaces to bring the rays together.
Same result, concentrated light, but two totally different ways of getting there.
Exactly. That's an important difference to remember.
And just like with the mirrors, where you put an object relative to a convex lens, changes the image you get. Real or virtual, magnified or diminished, inverted or upright.
It's true. There's a whole lot going on with lenses.
So it's like that image-forming game again, but this time, refraction is in charge. The textbook gives us another table, this one showing different scenarios for convex lenses.
Yeah.
Can we look at the case where the object is between the lens and its focal point? Isn't that how a magnifying glass works?
You got it. That's exactly how a magnifying glass creates a bigger image. And to see how, we can use another one of those ray diagrams. Okay, so we've got our magnifying glass scenario. We're still using those three special rays, right?
Right, makes sense.
So the first ray starts parallel to the principal axis, and after it goes through the lens, it bends, heading toward the principal focus on the other side.
Got it. Bending toward the focus. Second ray.
This one's easy. It goes straight through the optical center of the lens, no bending at all. Straight through the middle, simple as that.
All right, straight through the center, no detours. What about that third ray?
We aim this one toward the focal point on the same side of the lens as the object. After it passes through the lens, it comes out parallel to the principal axis on the other side.
Okay. So unlike the concave mirror, where those reflected rays seem to meet behind the mirror, these refracted rays from the convex lens are spreading apart. Where does the image form if they're not coming together?
Good point. They are diverging, but if you trace them back, they'd seem to be coming from a point on the same side of the lens as the object. That's where our virtual image is.
It's another optical illusion.
Yeah.
Our brains are filling in the blanks based on where the light seems to be coming from.
Exactly. And since that image is on the same side of the lens as the object, it's virtual. Can't project it onto a screen, just like those virtual images from concave mirrors.
And because the image is farther from the lens than the object, it looks bigger, right? Makes sense for a magnifying glass.
You got it. The lens is basically tricking your eye into seeing a bigger version of what's really there. Now, convex lenses bring light together, but concave lenses do the opposite. They spread the light out. The textbook says they always make virtual, upright, and smaller images.
So if convex lenses magnify, do concave lenses make things shrink?
You could say that. The concave lens spreads out the light rays, so the image looks smaller and farther away than the object actually is. It's like you're stretching out a big picture to make it look smaller.
So it's not that the object itself is shrinking, it's just how that concave lens bends the light, making it look smaller to us. What are concave lenses used for then?
They're actually used in some eyeglasses to correct nearsightedness. You see, in nearsightedness, far away things look blurry because the eye focuses the light in front of the retina instead of right on it. A concave lens in front of the eye can spread out those light rays before they go into the eye.
Oh, I see. So the lens helps shift the focus point back to the retina, making things clearer.
Precisely. It's like the concave lens is giving the eye a little help in getting a sharp picture.
That's pretty cool. Speaking of eyeglasses, the textbook also mentions lens power, something about diopters. What's that all about?
Lens power. It's basically how strong a lens is at bending light, either converging or diverging those rays. We measure it in diopters, or D, which is just the reciprocal of the focal length of the lens measured in meters.
So a higher diopter means a stronger lens, one that can bend light more.
Exactly. A lens with a shorter focal length will have a higher diopter, which means it can really bend those light rays.
Okay, that makes sense. So when my eye doctor tells me I need, let's say, a plus 2.0 D lens, that means...
That means you need a convex lens with a focal length of 0.5 meters to correct your farsightedness. The plus sign means it's a converging lens used for farsightedness. That's when things close up look blurry because the eye focuses the light behind the retina.
So the plus sign tells you it's convex, and the number tells you the strength, how much it bends the light. Pretty straightforward. And the textbook even mentions that our eyes themselves have a power of around 60 diopters.
It's true. The human eye is an amazing optical instrument. It's so complex.
It's pretty mind-blowing to think that everything we've been talking about, reflection, refraction, all these different mirrors and lenses, it's all happening right in front of us all the time. We just usually don't stop to think about the physics behind it all.
That's the beauty of optics. It's everywhere, shaping how we see and experience the world. We've just scratched the surface with this deep dive.
Yeah. From those basic ideas of how light bends and bounces, we get so many incredible things, like how a magnifying glass makes things look bigger, or how our own eyes focus light so we can see the world clearly.
And it really makes you think. We've talked about how lenses and mirrors manipulate light, but how does the eye, this biological wonder, adapt to different lighting? How does it adjust to let us see things both near and far?
That's a great question, and scientists are still figuring out all the answers. So if you're curious, keep exploring optics. There's so much more to discover.